Moving along in Chapter 7, let's talk about the center of gravity and the torque due to the force of gravity acting on an extended object. So remember that torque is a twisting force. It's a force that is applied to an object. Now we're no longer treating objects as a simple point. So it's a force that's applied to an object in such a way that it causes that object to rotate. So if I have my pencil here and I apply a force this way, it doesn't cause it to rotate. But if I apply a force this way, it does cause it to rotate. So this force exerts a torque. This force does not exert a torque because there's no lever arm through the pivot point here. Now, if I tried to balance this pencil on my finger here, it's going to fall, okay? And that's because the center of gravity of the pencil is about here at the center. So there's a force acting downwards here that is causing it to rotate. If I place the pivot underneath that center of gravity, if I can do it that way, it's not rotating. That means that the force of gravity acting on this pencil is got zero lever arm. It's got no lever arm so that the torque is zero. Now, of course, there's gravity acting on all of the pieces of this pencil all the way across from here to here to here to here to here. And each one of those little bits exerts a torque. But the gravitational force on this side wants to make the thing rotate this way. I don't know if that looks like clockwise or counterclockwise to you. But the forces acting on the pieces on the other side of the pivot are trying to make it rotate the other way. So those are opposite sign torques and they add up to zero. So there's always, for any given object, a point that you can consider to be the center of gravity, and all of the force of gravity on that object can be considered to be applied at that point, at the center of gravity. And so if my pivot is located at the center of gravity, then the net torque is zero because the force is applied there, and the distance from that force to the axis or the pivot point is zero. So the lever arm is zero, so the torque is zero. So that's what's explained going through the first few parts of the slides here in section 7.4. Here we see a gymnast, and the center of gravity is in the torso, and so the torque on her body is due to that force of gravity acting on the center of gravity. So let's consider, how do we actually calculate the location of the center of gravity? Well, as we just saw, the torque on an object is zero, the gravitational torque on an object is zero if the pivot point is at the location of the center of gravity. And so that means, as you see in the slide here, if we consider sort of a dumbbell that's asymmetric with a mass m1 on the left and a mass m2 on the right, that the gravitational torque on m1 is the force of gravity on m1 times that distance r1, and the gravitational torque on m2, the torque due to the force of gravity on m2, is the weight of m2 times that distance r2, the distance of m2 from the pivot point. And so if the pivot is at the center of gravity, those two torques must add up to zero, and that's what's shown in the equations on the left-hand side of the slide. And when we solve those, we get an expression for the location of the center of gravity. See if I can write here. Sometimes it's also called the center of mass. I think the book is very careful about always calling it the center of gravity. I may slip up and occasionally refer to it as the center of mass. But the location of the center of gravity for a one-dimensional object is the sum of the position of each piece of mass in that object times the amount of mass in that piece of mass divided by the total mass, which I'll write as the sum of those m sub i's. So this equation that I've written here is equivalent to the equation on the slide as long as there are just two pieces. I should have connected my I had my AirPods in, but I wasn't using them. Uh, what that means is that these subscript i's refer to how many different bits there are in a mass. So let's do an example to illustrate how we would calculate the center of gravity for an object. So let's do chapter 7, number 35, which says to calculate the center of gravity of a group of 3 identical coins that are on 3 corners of a square 10 centimeters on a side. So let me sketch it. So we have a weird L-shaped object like this. This distance is 10 centimeters, and this distance is 10 centimeters. And we'll have this be the x-axis and this be the y-axis. And the question is, where is the center of gravity of this object? And because this object is two-dimensional, there will be both an x position and a y position for the center of gravity. So we're going to place the origin at the lower left coin. We're free to place that anywhere. It's just a point of reference, okay? So we're going to have the origin be here. That means x equals 0 and y equals 0 at that point, okay? So we're not given the mass of these objects, but based on our expression here, we have xcg, xcg is, I'm having trouble with all these things, is the sum of the x positions times the masses of each thing divided by the sum of the masses, and the y coordinate of the center of gravity is going to be similarly the sum of the y positions times the masses divided by the total mass. So let's start off, let me make this thing go away. Let's start off with the x positions. So xcg is x1 times m1 plus x2 times m2 plus x3 times m3 divided by m1 plus m2 plus m3, and we are given that m1 equals m2 equals m3. The coins are identical, and so let's just go ahead and say, let's call that m, etc. So then the x coordinate of the position of the center of gravity is x1 times m plus x2 times m plus x3 times m divided by m plus m plus m, which is just 3m. Then, what are the positions? What is x1 equal to? Let's redraw this thing and number our coins. So let's call this one number 1, this one number 2, and this one number 3. Doesn't really matter, that's just sort of arbitrary. So the position of the x coordinate of coin 1 is 0. It's at the origin. The x coordinate of coin 2 is 10 centimeters. It's out here 10 centimeters away, remember? And the x coordinate of coin 3 is also 0, okay? Remember that This is our x-axis, and this is our y-axis. So coin 3 is on the x-axis, so its x-coordinate is 0. So that means that the x-coordinate of the center of gravity is just 0 times m plus 10 times m plus 0 times m over 3m, or 3.33 centimeters. The m's cancel, and we can see that we didn't need to know the masses because they're all identical. The y-coordinate of the center of gravity is y1 times m plus y2 times m plus y3 times m, again divided by m1 plus m2 plus m3, which is just 3m. So that gives me, what's the y-coordinate of coin 1? It's 0. It's at the origin. What's the y-coordinate of coin 2? It's also 0 because it is on the x-axis, and so its y-coordinate is 0. I think up here, when I was talking about the x-coordinate of coin 3, I may have misspoken. It's on the y-axis. Its x-coordinate is 0. Anyway, the y-coordinate of coin 2 is 0, and the y-coordinate of coin 3 is 10. And so we get the same thing. YCG that we got for x is 10 over 3, and the m's cancel, so it's 3.33 centimeters, and that's the location. So notice, if we were to plot that, that would be around here. This is the center of gravity up here. Draw that better. Go out about a third of the way, up about a third of the way, and that's your center of gravity up there. So if this were actually, like, if we didn't consider that these coins were connected by anything with any mass, but if you had an L-shaped object, then you would get a center of gravity that's not actually inside the object itself. It could be in some point in space that's not actually part of the object itself.